Okay, so let's start on the clock. First talk is by Roni Ilan, Topological, superconductivity and conditions for gas nanowires.
Thank you. Hi, everyone. I'm Roni Ilan. I'm from Tel Aviv University, and today I want to talk about plain old three-dimensional topological insulators, from topological insulators. And I want to discuss these systems as we pair them with S-wave superconductivity and what the conditions are to get a fully gapped topological superconducting state in wires made from 3D TI. So the physics that I will talk about appears in two publications. One is already quite old, from 2014, and in this paper we looked at what would be transport signatures in order to detect topological superconductivity in 3D TI nanowires. And then a more recent one that appeared a few months ago and was published in SciPost discusses what are the conditions to get fully gapped state in these wires, and apparently it's not so trivial. So both works were done in collaboration with Fernando de Juan, who is there in the back, and also with Jens Barderson from KTH, and we had multiple discussions with Yong Chen from Purdue, Marcel Franz, and John Moore. I want to thank them, and I want to thank the organizers for the opportunity to present these results here. Okay, so here's the outline for what I'm going to do now. I'll start by discussing the normal state in TI nanowires, because it's a bit different than just slabs or large systems. So I'll talk about TI nanowires in the normal state, and I'll talk about how flux affects the band structure of the surface states, and how it can cause the parity of the number of modes to change and lead to effects like perfect transmission, for example. Then I'll talk about topological superconductivity in quasi-1D, and I'll talk about the topological invariant that characterizes this system, and what are the potential transport signatures for this state. And then I'll go into what the conditions are to get the topological superconducting state in TI nanowires. I'll talk about conditions for the formation of a fully gapped state, and also on the conditions for the formation of a maximally gapped state. So those are not quite the same, and what plays a big role here is rotational symmetry, and so I'll discuss continuum models versus lattice systems. Towards the end of the talk, I'll compare this with very well-known platforms for the formation of 1D topological superconductivity, spin-orbit coupled wires, and I'll say a word about experimental states. Okay, so I'll start by talking about normal 3D TI nanowires. So what I want you to think about now is the simplest system imaginable. Then you take a 3D TI and you form it into a perfect cylinder. Okay, so this system has perfect rotational symmetry around the axis of the cylinder. It's characterized by two coordinates. So there's the x-coordinate along the wire, and there's an angular coordinate theta that wraps around the wire. And it turns out that the Hamiltonian for this system is really simple. It's very similar to the one that you would have for a flat surface state, but there's one difference, which is that the boundary conditions of the wave functions as they wrap around the wire are antiperiodic. Okay, and the reason they're antiperiodic is because it's spin momentum locking. Basically, you take a path around the wire, then the spin rotates, gives you a pi Berry phase. Okay, so angular momentum is quantized by half integer units, and that's very important here. So this system has a very nice tuning knob, which is that you can thread flux through the cross-section of the wire, and I want you to imagine that the magnetic field can be completely parallel to the surface states. Okay, so it doesn't gap it in any way. What it generates is an Aronoff-Bohm effect. Okay, so if your particle runs around the wire, it sees the flux, and that creates the change in the spectrum, essentially. Okay, so what I'm going to do now is I'm going to contrast the spectrum in the absence of flux and in the presence of flux. Okay, so if you have zero flux through the wire, this is the band structure, and it has a gap. Okay, it's gapped because of the pi Berry phase, and these bands are angular momentum resolved bands, and they're all doubly degenerate. Okay, there's double degeneracy between plus and minus. Okay, and now on the right-hand side, what I'm going to do is start increasing the flux from zero. So we break time reversal symmetry. The first thing that happens is that the degeneracy of the bands is lifted. Okay, and as you increase the flux, it lifts more and more. And then as we move towards half-a-plus quantum, something very interesting happens, namely that all the upper bands are still doubly degenerate, but they switch partners. Okay? And we are left with one mode that is gapless, linearly dispersing, and is not degenerate at all. Okay, so this is a singly degenerate band, which basically means here, and this has a strong consequence, that it doesn't matter where you put your chemical potential, as long as it's in the bulk gap, you have always an odd number of modes. Okay, so there's an odd number of modes. So half-a-flux quantum through the wire results in an odd number of modes at any energy. Also, the system at half-a-flux quantum has effective time reversal symmetry. The scattering matrix is antisymmetric. These two properties, if you combine them, you can show that there is also, in the presence of disorder, a single mode that is perfectly transmitting through the system. Okay, that's not an essential point for this particular talk, but it's a very interesting property of the system that basically tells you that the two-terminal conductance for the system is bounded from below by E squared over H. Okay, so this is a very idealized model, but actually some of these properties have been seen in experiments already. So these are two examples out of several. This is an example from Nadia Mason's group, and this is an example from Yong Chen's group. What you're seeing here are basically Aronoff-Bohm oscillations as a function of flux. And the way you would think about this is you want to fix the chemical potential to some value, let's say in the absence of flux. All the modes are doubly degenerate. You have an even number of modes under the chemical potential. Then you start changing the flux, and what happens is that the parity of the number of modes switches from even to odd, even to odd. Okay, so this causes oscillations in the two-terminal conductance. And that's what you're seeing here. Okay, so this physics is relevant for realistic systems. Okay, so how does this relate to topological superconductivity? Let me just remind you what the conditions are to get a topological superconductor in 1D. What you want is a fully gapped 1D superconductor that supports isolated Majorana zero modes at the ends. Okay? And in order to make one, what you want is to add pairing, S-wave pairing, that's the way to engineer it, to a 1D system that has an odd number of modes. This is basically the Kitaev criteria. Okay? So this band structure here is for the spin-orbit coupled wires, and I'm sure you all know this. This utilizes spin-orbit interaction to resolve spin degeneracies, and then a Z-man gap to create a scenario in which you can put the chemical potential and get a single mode. Okay, so, but what I've told you right now is that we have an alternative way. There's an alternative system that gives you this odd number of modes quite naturally, and you don't need to worry so much about where the chemical potential is. Okay, so here's the recipe, and this proposal was already put forward by Cook and friends quite some time ago. What they said basically is you take the wire, you thread flux rate, you get an odd number of modes, and you put proximity effect. So you imagine taking this wire and laying it on top of a bulk superconductor, niobium, or whatever, that induces proximity effect. These wires are typically a couple of hundred nanometers thick, so comparable or smaller than coherence length of typical superconductors. So this is quite realistic. And then, if you could, you would want to probably interface superconductivity and some magnetic regions pointing in the right direction, and then you have the potential of binding Majorana zero modes at that interface. Okay, so we set out to think how you might detect topological superconductivity in the wires. And here's how you do this in 1D. Basically, you want to think about scattering states. I'm going to talk about ballistic wires. You know disorder. These are clean wires. So you look at incoming and outgoing states, and what you calculate is the scattering metric. And from this, you calculate the conductance across a normal superconducting interface. Now, in 1D, the conductance across such a junction is actually pretty unique. So if you're in the single mode regime, it's actually representing a topological invariant. This was shown by multiple groups. The conductance is either quantized exactly at 0, or is quantized at 2 e squared over h. If you have a trivial superconducting state, it could be quantized at 0. Otherwise, you get processes that are called perfect and rare reflections that lead you to this 2e squared over h plateau. Okay, so this is what we set out to look for a few years ago. And so we simulated this for the TI wire. Basically, we took the TI wire, we put this interface between superconductivity and nothing, just a normal region, and calculated the conductance. So here is the band structure in the absence of flux, it has a gap, and here is the conductance that we computed, and as you can see, it's quantized at 0 when you're in the gap, and then starts increasing in steps of 4e squared over h, because you keep adding an even number of modes. Then we threaded flux through the wire, we closed up the gap, we have the single mode regime here, and we see that we get a very nice 2e squared over h plateau, as you would expect. Okay, so this would be a nice signature. However, we also found that it's not enough to thread half a flux quantum through the wire. You also need to do something else, which is that you need to wind the phase of the order parameter around the wire. Okay, so half a flux quantum is not enough. You also need a vortex to run along the wire. And the way we saw this is that when we had half a flux quantum here, we didn't get any quantization plateau. Okay, we saw some mass of crap, whatever. And then only when we twisted, we saw this 2e squared over h. So it seems like the vortex plays a pretty crucial role in getting perfect and rare reflection. And the question is why? Okay. So before I tell you why, I want to tell you how you plot the phase diagram for this system. And this was already done by Group in France. Some time ago, we reproduced this. Basically, we calculated the topological invariant for this Hamiltonian. This is the Google-Gen Hamiltonian for the system. Coupled to superconductivity, we have a fair potential here with the phase wind if we wanted to. And I'm contrasting here the situation between having a vortex and not having a vortex. Various values of the flux and various values of the chemical potential. So you stare at this for a bit, and you realize that the two phase diagrams are essentially the same, right? So non-trivial topological invariant. I'm not going to go into the technical details of how you calculate it, but if the sign is -1, it implies a non-trivial phase. So these are the dark blue regions here, and they're basically in the same place in parameter space. Okay, so you only see minor changes in the phase diagram when you compare vortex and non-vortex. So we were kind of scratching our head and thinking, what's going on? This was consistent with previous results, and then we realized that we actually need more information. And the information comes from the band structure itself. Okay, so now I'm going to look at the band structure and compare phase winding and no phase winding, and you'll see immediately what happens. So this is two identical spectra. Okay, basically this is a Google-Gen spectrum in a single mode regime, but the gap magnitude is 0. This one doesn't have phase winding. This one has phase winding, but you can't see the difference because the gap is 0. Now I'm going to add a finite pairing potential. And as you can see, if you don't have a vortex, the spectrum remains gapless. Okay? But if you do have a vortex, you've got a finite gap. So that's the essential difference. It's not enough to look at the topological invariant. You actually need to check if you have a gap in your system. Okay? So the continuum model that has full rotational symmetry, and that's important, needs proximity effect, needs half flux quantum, and a vortex to get a fully gapped topological superconducting state. Okay, so then the reason for this is actually quite simple to understand. While the spectrum is identical in these two scenarios, the quantum numbers are not. Okay, because what I can do is I can perform a gauge transformation that changes the boundary conditions for the particles as they wrap around the wire. This shifts the angular momentum state from being half integer to integer, and allows you to match particle and Hall states in at the chemical potential and pair them. Okay, so before we go into that more deeply, I want to show, to kind of correlate this phase diagram of the topological invariance with the gap. Okay, so here's the information of the gap. And you can clearly see the difference from here, okay? In the absence of a vortex for this system, there's complete anti-correlation between the location in the phase diagram in which the topological invariant is non-trivial and where you have a finite gap. However, if you add a vortex to the system, you completely shift this gapped region to be perfectly correlated with the non-trivial variant. This doesn't depend on the details. This is essentially the same figure, just a different magnitude of the gap. And again, you have this anticorrelation versus perfect correlation. Okay, so the vortex is essential, and the reason it is essential is because in the absence of phase winding, there's just a mismatch of 1 unit of angular momentum at the Fermi energy. Okay, the particle states here have angular momentum 1/2, and the whole states here have angular momentum -1/2, and then what the vortex is doing is basically it's compensating for this mismatch.
Sorry,
Okay.
what? That
Yeah.
gap above at like 2 million volts.
Yeah.
That's a delta gap. Right?
It's a gap, yeah.
So what happens if I increase delta?
If you
Why can't I pull them?
I mean, you probably can, but you're limited by the size of the pulse.
Right, but that large delta, I could pull them. That's a
Potentially
true
you could.
statement.
Potentially you could. Okay, so until now I've discussed quite an idealized model, right, that has full rotational symmetry. We don't have cylinders in reality. What we have are lattice systems. So you might ask yourself how relevant this is to the realistic systems. And then we are going to look now at the role of discrete rotational symmetry versus continuous rotational symmetry. So the difference would be that if you have n-fold rotation axis, that makes your angular momentum be conserved only modulo n, okay, not entirely conserved. And it turns out that it's still possible to enforce a completely gapless state even in the presence of n-fold rotation axis. So one simple example is this situation in which you have a mismatch of 1 unit of angular momentum. Basically, if you have a 2-fold rotation axis in your system, your set would still be gapless. But these are not identical. Okay, if you increase the flux, you go to 3/2. You need the half integer units to get an odd number of modes. You go to 3/2, the mismatch becomes 3. And then again, if you have a 2-fold rotation axis, you would still get a gapless state. However, if you have a 3-fold axis, then those states are identical and you can pair them. Okay, so it's important what the symmetry is. The general statement would be that if you have an even-fold rotation axis in your system, you get a gapless topological state if you don't wind the order parameter. Okay, so it's quite crucial. Okay, so I talked about the conditions of when you pair and when you don't pair at the chemical potential. Now I want to talk about how reducing the symmetry affects the magnitude of the gap, because that also has severe consequences. So what I'm going to do is I'm going to demonstrate phase diagrams on a particular lattice model. So it's this one if you care about the details, but the essential thing to notice here is that we're choosing a model that has C4 rotation symmetry. Okay? So then if you have a geometry that respects that rotation symmetry, then there is this anticorrelation between the position of the gapped states and the non-trivial topological invariants. Okay? And everything that I'm showing here is in the absence of a vortex. What I want to ask is the following question. If I start reducing the symmetry of the system, can I still get a gapped state even though I don't wind? And what is the magnitude of the gap? Okay? So you can see a small gap developing here around flux 2, and that was not allowed in the system that was perfectly rotational symmetric. This is because of the C4 symmetry. But this gap is trivial, so nobody cares. Okay? So now I'm going to reduce the symmetry further and go to a system that has only C2 rotational symmetry, and as you can see, there are more kind of faint gaps appearing here, which is expected. But again, they are trivial. Okay, so you never get a topologically gapped state here. Then you get rid of the symmetries entirely just by choosing a weird cross-section, let's say a triangle. And here you can already see an effect. Basically, you get gaps everywhere, but they can be very small. Okay, so you can get topological gaps here, but they're not very impressive. They don't come near to the bulk superconductivity. And then the final column here what we simulated here is an inhomogeneous pair potential. Okay? And that's already approaching a realistic system. Because if you want to take your nanowire and place it on top of a bulk superconductor, then you would assume that in the regions that are closer to the superconductor, superconductivity is going to be larger, so the induced gap would be larger, and as you move away, the gap would be reduced. So that also breaks rotational symmetry, and that also gives you gaps, but they are still small. Okay? So now we want to see what the role of phase winding is in systems that have reduced symmetry, and whether that gives you some advantage. Okay? So now we're going to break rotational symmetry in various ways and contrast the situation between having phase winding and not having. So this is again a clean wire. This time it's a discrete lattice system. So for the clean wire, you get the situation in which you have, in the absence of a vortex, a large gap that is perfectly trivial. Then you add a vortex to the system, and then your gap shifts, and it shifts to be correlated with a non-trivial topological invariance. So this gives you a 1D topological superconductor with Majorana's and whatever you want. Then breaking rotational symmetry, one example is creating an asymmetric supercurrent profile. The way you would do that is just by, so we add a magnetic flux, we add through a parallel substitution to the lattice model. And if you are in a normal state, you're free to choose the origin of this vector potential wherever you want. It's just a choice of gauge. But if you have superconductivity, that already matters. So I can offset the origin of this vector potential. That would generate kind of asymmetric supercurrent profiles in the system and break the rotational symmetry. So you want to look at this. This is in the absence of a vortex, and in the presence of asymmetry, you get a large trivial gap and very, very small non-trivial gaps. However, if you phase wind, then you can get a significant gap shifted to the non-trivial regime. And now what I'm going to do is I'm going to talk about disorder. Okay, just plain disorder, nothing funny. And the way we introduce disorder into this model is by introducing a random chemical potential. So this is some random chemical potential drawn from some uniform distribution, and we look at two strengths of randomness. So the strength of the disorder here is kind of small, which means that you can still talk about angular momentum. It's kind of a good quantum number, but not entirely. So in the absence of a vortex, again, you get a large trivial gap. But if you phase wind, you can shift that gap into the non-trivial regime. However, if you increase the disorder strength and make your angular momentum basically a bad quantum number, then you already get rid of the distinction between the two. Okay, so disorder can be beneficial if you don't want to wind your phase, but if your system is rather clean, which you want to get nice interfaces and whatever, you want to have a vortex thread through the wire. So now comes the practical question. How do you actually stabilize a vortex configuration? So then what we propose, and this is consistent with results from experiments that I'll talk about in a minute, is that you want to encase your TI nanowire in a full shell of superconductivity. And the reason is, if you lay your TI wire on a superconductor, you get this inhomogeneous pair potential, but there is no particular reason why the flux will induce a vortex in the system. However, if you have a full shell encasing your TI wire, then the energetically stable configuration at half a flux quantum is that of phase winding. Okay, so you want to be in this situation. How much time do I have?
2 minutes before 10 minutes.
Okay, very good. So now I want to summarize this part before I go and say a few words about experiments in other systems. Basically what I told you is that in clean TI nanowires with continuous rotational symmetry, a vortex is crucial to get a topologically gapped state. In clean wires with discrete rotational symmetry, a vortex is still crucial to get a topologically gapped state. However, in wires where you break rotational symmetry, the vortex is not essential, but it will almost always give you a bigger gap. Okay, so this is what you want to have. You want to be in this situation and not in that situation most probably. And now, whoever's been following the debate about how to induce superconductivity in 1D wires, maybe have seen a couple of works that came out recently from the groups at Station Q. So there was a theory paper that claimed essentially the same, that you want to have full shell superconductivity even in indium arsenide wires. And so here's the essence of what they're doing. They're writing down a model for a cylindrical nanowire in 3 dimensions. This term kind of looks the same as what we have, only in 3D. And then there is an added p-squared term. And then if you were thinking that your particles could be confined to the shell of the wire, which could happen for electrostatic reasons, you can map this model onto the model of Oregon-Luchin. Basically, this kind of plan structure would appear if you're in the zero angular momentum state. However, all the parameters in this model are renormalized parameters. Okay, so the chemical potential is an effective chemical potential that depends on various parameters of the system, like spin-orbit coupling, flux detuning from half-flux quantum. Also, the Zeeman coupling depends on this flux detuning. And if you want to get phase winding, then you want to be around half-flux quantum, so this would be a small quantity. So basically the difference between this system, in which you want to kind of nail your chemical potential into this gap, but it will depend on various parameters. This system, compared to ours, has a slight disadvantage in the sense that we don't care what the chemical potential is. Okay, as long as it's in the bulk gap, you'll have an odd number of moles, and there's no need for tuning. And this is important, particularly if you have a full shell superconductivity, because there you lose the ability to properly gauge your system and play with the chemical potential. Okay, you have less freedom to do that. Okay, so this has an odd number of modes for any chemical potential. Okay, so this is my final slide. I want to say something about experiments. So it has been demonstrated that you can successfully couple TI nanowires to superconductivity. This is from Yong Chen's group. Basically, what they're doing is they're inducing proximity effects, and they're creating a Josephson junction, and they did observe signatures of multiple Andreev reflections in these junctions. There's no threading of flux yet, but we're hoping that this is going to happen in the near future. And down here, there are the new experiments for Charlie Marcus's group, and you can see a really nice superconducting shell around an indium arsenide wire, and they do trap a flux to it, and they do phase wind, and they seem to have very nice in-gap states developing around half-flux quantum. Okay, so this seems to be consistent. And with that, I want to conclude. So I talked about conditions to get fully gapped topological states. So topological superconductivity in TI wires requires flux and phase twisting. And then practically phase twisting you would get, or it's more likely to get if you have full shell superconductivity. And I want to end by mentioning some open questions with these wires. So they seem to be kind of a promising platform. However, there isn't much discussion about how you would braid Majorana end states. So if these wires are finite, there is a magnetic field that penetrates the end of the wire and creating a Majorana state there. And it's not entirely clear how you would manipulate these Majorana modes. That's kind of difficult here. I guess it's difficult in any system. So if you're interested in this kind of system, I'll be happy to talk about it. And so I'll leave you with that. Thank you.
Questions? 5 minutes.
So you were saying if you break crystal symmetry, you can get smaller gaps. Are those gaps still topological? Could you make them, or they're not topological
That
gaps?
That depends. If you have reduced rotational symmetry, but still some rotational symmetry, you are likely to get a gapless state and this phase one. If you break the rotational symmetry completely, you can get a topological gap, but the size of the gap will depend on how you broke the symmetry, how big the perturbation is.
If the symmetry breaking is big, could the gap get to be as large as you wanted it, or is there some limitation?
It depends on how you break the symmetry, but it always appears to be smaller. Okay, we haven't checked all possibilities, but I guess, I mean, for example, I would consider large symmetry breaking this triangular cross section. You know,
Pretty
that's
large.
pretty large.
Yeah.
But then the gaps are still smaller than if
Yeah.
you. than
I
states
see.
in the
So you're
two-phase.
breaking symmetry by the shape of the wire.
That you could do that.
But maybe if you had
that way.
the crystal actually properly having broken symmetry, it might be larger effect than breaking it with termination.
Right. I mean,
Maybe.
that takes checking the details.
Yeah,
I
it's a
guess, of
detail
whatever
question.
material you
Yeah.
have.
But if you have the superconductor fully around the wire, then symmetry doesn't matter anymore.
Symmetry doesn't matter if you trap the flux and you in
Yeah.
phase one, then your symmetry cannot enforce.
Could be very naive, but have you thought about wrapping your wire in a superconductor with a non-trivial order parameter symmetry so that you relax the vortex condition, but you phase wind because of pairing?
The short answer is no. I haven't considered. So you want to induce
So you wrap it in a
some
P-wave or
non-trivial
something.
superconducting states.
Yeah.
I don't know what role the Dirac surface states would play here. I mean, I guess it's possible if you're replacing phase winding by some non-trivial order parameter, it might be. I haven't thought about it.
It just sounds from a, okay, so wrapping it in a P-wave superconductor sounds hard because, well, probably you
You
don't
need
have
a
any.
P-wave
But then again, also from a device perspective, to have this wire and then trap exactly one vortex in it, no other vortices, and so it does sound really, really hard to make. If you could have if you could replace this with a vortex-less state, that
So it sounds hard, but then again, it's been done. You know, so the energetically stable configuration and half a flux.
well, the question is what you want. Do you want one wire and tune this, or do you want a chip with 1,000 or millions of them? Then
For me, Microsoft.
Wait, but what's been done to? They
To
didn't
thread,
put a
so-
vortex. They put. Was it just flux? What was the charges?
They put flux,
Right.
and then they see an in-gap state, and presumably that's because you wind. I mean, that the theoretical model tells you that if you wind, you pair, and if you don't.
Do they see that kind of like in all wires, or it's kind of like some subset of them? Yeah, who knows?
Papers,
a
yeah.
typical wire shows.
Yeah.
No, the papers are a very nice result. They have very nice, in-gap state. So, if you grow your wire correctly and you manage to.
Can I go back to this gap and vortex figure?
Which one?
The one where if you don't put a vortex, you don't gap.
This one?
No, just the lens.
This one?
Yeah, there was a comparison, but this one's perfectly fine too.
Okay.
So this one is a one-dimensional gapless superconductor.
Yes.
Normally, like, there's no, right, this is kind of a, normally, gapless superconductors are in 2 dimensions because the order parameter goes to 0. You need at least 2 dimensions for a gapless superconductor. But this guy certainly says pairing away from the 0 energy.
First of all, this is one-dimensional in the sense that, you get many things here that you don't get from a strictly one-dimensional system, right? It's still a 2-dimensional surface of a higher dimensional system.
That's fine, but it's got quantization, so like I
Yeah,
think of it
yeah,
as.
yeah.
But what you're saying is that as I tune the gap from 0, I will stay in a metallic superconducting state until that gap is whatever, order 5 electron volts, where I completely pull it apart. Any more questions? Nice thing, Roni, again.